While we've been getting great observations from the James Webb Space Telescope, it just doesn't have what it needs to be able to distinguish Earth-sized worlds orbiting around sun-like stars. It's not about the brightness that has plenty of collecting power. It's the ability for James Webb to resolve the gap in between the star and a planet. For James Webb to be able to observe an Earth-sized world orbiting around a sun-like star in the infrared wavelengths that it operates, it needs to be about 21 meters across, which is a much bigger telescope, bigger even than the largest version of LUVOIR. If you're going to go into the optical, then the telescope can be smaller, but there's some real advantages to observing at the infrared wavelength because the brightness of the star is much less compared to the brightness of the planet, and so you don't need as powerful a coronagraph. You just need a bigger telescope. But do you need the whole telescope? Maybe you could just use a slice of the telescope that gets you that 21 meters across, and then you don't need all the rest of that telescope stuff. My guest today is Dr. Heidi Jo Newberg. She's a professor of astrophysics at Rensselaer Polytechnic Institute. She was awarded a NIAC grant to develop a different kind of interesting telescope, and then sort of the work on that telescope led to this new idea. Instead of making a giant round telescope like the shape of James Webb or the Habitable Worlds Observatory, what if you just make a thin slice of a telescope that gets you enough of a baseline that you can resolve a planet compared to its star and in the infrared, and you don't need that really fancy separate sun shield coronagraph. So if this idea is intriguing to you, enjoy this conversation with Professor Heidi Jo Newberg. Heidi, it's good to see you again.
Hi, it's good to see you. Good to be on your show.
And I think you are probably one of the quickest turnarounds in interviews. I will often bring guests back for a second round, but in this case, you triggered what is my favorite topic twice, which is a really cool idea for a telescope that's going to allow us to see Earth-sized worlds orbiting around sun-like stars. That if you released one of these papers every month or so, you would just be my regular guest once a month, because that is catnip to me. So we'll talk a bit more about the previous telescope and the NIAC grant, and we did an interview here on the channel, but I want to focus right now on the new idea, which is that you're proposing a dramatically different telescope shape as a way to help us try and resolve that Earth 2.0. Can you explain this idea?
So it's a very simple, actually. The basic idea of finding exoplanets is that you have this star like the sun, it's very bright, and then you have a planet like the Earth, not so bright, and you would like to see the planet and extinguish the star, right?
Right, and we're dealing with like 1/10,000,000th the light. Like
so that's part of the equation, is that in the visible, you're correct. It's 1/10,000,000th of the light of the sun if you look in the wavelengths that we see with. But if you can look in the infrared, then it's only more like 1,000,000. And so one of the things that we were looking at, actually in the original NIAC grant and in this one, although it's not required for this, is probably better with infrared, because it's only 1,000,000 times, and it's much easier. We have the technology to extinguish something that's 1,000,000 times brighter than an object, but not for 10 billion. We don't know how to do that at this time. And so we want to look in the infrared, and there's a very simple physical principle that we physicists learn in our first year of college. One of the things that we learn right from the beginning is that if you want to resolve two objects, you want to see that there's one here and there's one over here, and they're not merged together. You have to use a telescope or an optical system that is larger for the larger the wavelength you are. And so the size of the optics, the angle that you can resolve is tangent of the angle is proportional to the wavelength. So it's bigger if you have a bigger wavelength over the diameter of the telescope. So if you want to be able to resolve two things, you need to have and you want to use a long wavelength. And in our case, long is 10 microns. Might not seem very long to you, but it's a lot shorter than the light that we see at.
Yeah, the nanometers.
Yeah, nanometers. And so you have to have a very big telescope. And so this very simple calculation tells you that to see something that is a distance of 1 AU, which is the distance from the sun to the Earth, at a distance of 10 parsecs, which is about 33 light years, which is about as far as you could imagine having a planet that you could send a probe to, maybe communicate with, that kind of stuff. Those ones you really want to interact with. So if you put it that far away and have it be 1 AU and you want to look at 10 microns, it's a very simple calculation to show that you need a telescope that's 21 meters across.
Huh.
And that's the thing.
So that's it. And that's
it. You need something 21 meters across. And we know that it was really hard to get that JWST telescope there, and it's 6.5 meters across. And so this has been like a bottleneck for finding exoplanets that, some of the original exoplanet designs wanted to put a bigger telescope up in space so they can get the higher resolution and they don't have to have these very high performance coronagraphs. And so what this concept says is the physics all says you need 21 meters across. But it doesn't say that you need to have 21 meters in every direction. And so usually people think about telescopes as being round. They have a round mirror. And if you make a 21 meter round mirror, it's extremely big. But if you made a 21 meter mirror that's 21 meters in one direction and 1 meter in the other direction, that's not so big. You can kind of imagine just kind of folding it up and then folding it out like JWST, so you could get something like that up there.
Yeah. So like my understanding of this sort of like telescopes in general, we talk about this idea of interferometers, that you could put two telescopes side by side, separate them, and that gives you that baseline of the separation of the telescopes.
Same idea.
But the reality is that all telescopes are interferometers.
Yeah,
that they much. Just also have all the in-between space as well.
That's right.
Right. And so if I come to you as a NASA administrator sometime in the future and I say, I want to build a telescope that's going to allow me to see Earth 2.0 in the infrared, and it's a 20-meter telescope, you can just go, nope, I'm not interested, because it doesn't meet that perfect 21 meter minimum size. That's what you need to get you into the ballpark to start doing that resolution. I can decrease the wavelength size, so I can say, okay, fine, let's push it into the visible.
That's right.
Now you're interested again, but then you want to know about the coronagraph that I'm bringing to the table, because we need to be able to block that light. So it's that balance between those things. And the traditional idea is let's just build an interferometer, but also that's an incredibly complicated idea, and the challenges of keeping them.
There are two big ideas that people are using, both related to blocking the light. One of them is to use an interferometer. So you have smaller telescopes, but you move them very, very far apart. And the issue with that is that they have to formation fly really, really well. I was calculating that atoms bumping into them are going to take them off. And I was like, then you're going to send out another atom to try to push it back. And I couldn't really wrap my head around that. And the other one is to block the light. You look at probably star shades and things like that. And so in that case, you have a really good coronagraph that you can, if you fly this thing very far away and you make a very big thing and it blocks out just the light from the star, you can work on doing a really good job of blocking out about that star. But we're talking about kinds of things like flying this thing like 17,000 kilometers away kind of distances, and then you imagine trying to then look at another object. And this thing's going to have to fly, 10,000 kilometers across the universe. And I looked at that and said, that's nuts too. So they just seem like really crazy crazy ideas, to me.
Right. And so instead, let's just build a telescope that has 21 square meters of
21 meters long. Yeah, let's just do that.
Just make it 21 meters.
That's
20 meters
what I'm
long and
saying.
1
Just
meter.
build-
20
just
meters
build
long
them
and
20
1
meters
meter
long.
wide.
Yeah.
Yeah,
1 meter
yeah.
wide.
And so is there any specific mirror shape, or would it just be the same thing? Would it just be a segment of standard parabolic or spherical mirror shape?
Yeah, well, the one that we, just sort of put out there as a straw man was to take JWST, scale it up to be 21 meters, and then just carve out a piece of it right down through the center that was 1 meter wide. And so you just take that, and you can imagine building it in with 1 meter by 1 meter segments, just as JWST is segmented, and putting them all together. So you have 21 of these, sorry, maybe 22. An even number would be good. But the downside of this long, thin telescope, there's always a trade-off, right, is that the images that it produces will not be round. So stars, if you take an image of a star, it won't be round. It's going to be very narrow in the direction where the telescope is long, and it's going to be very fat in the direction where the telescope is narrow.
And if I did this, like if I just masked off my telescope mirror, I would see a similar thing.
Yeah. Well, let me clarify that. The answer would be yes if your telescope was in space, or yes if your telescope was a radio telescope.
Okay.
But in optical telescopes on the Earth, they're not limited by this diffraction limit. They're limited by the atmosphere of the Earth spreading the light out. And so in that case, the atmosphere is the same in both directions. So if you went out to your backyard telescope and you did this, no, you wouldn't see that because it's not diffraction limited.
Right. Once if I destroyed the atmosphere, then I would start to approach the diffraction. Okay, I understand.
If you got rid of the atmosphere, then that would.
Right. And so then this sort of look at the object that you're looking at appearing a different shape depending on the orientation of the telescope. So I'm assuming that you want a perfect alignment between the telescope and the position of the planet compared to the star.
Yes, that's exactly how it works. So if you don't know where the exoplanet is to begin with, so you're on a mission to find exoplanets, then you can look up at the star, and you have your telescope this way, and if the planet is the same direction from the star that's as aligned with the telescope, you're good and you see it. But if it's not, if it's the other way, then you would have to rotate the telescope in order to see it. And so for finding a planets at any orientation, you have to rotate it. And so you can either just rotate it slowly, which has some advantages because the telescope is just doing that. You don't need to be using fuel to do that. It's rotating around and looking at it. Once you get in position, it can just do that and then sweep out, trying to see at all different angles. Or it actually would work almost as well, but maybe use a little more fuel to look at it this way and then just look at it 90 degrees away. Because then you're going to search an area around the star that is a square. If you did it by rotating it slowly, you would sweep out a circular area around the star that you're looking. And those are pretty, a square and a circle inscribed in a square, you don't lose too much with the two things. But in terms of how this works, that's going to be set by, engineering constraints on how the control system for the telescope works. But yeah, basically, if you turn it, it takes a little more. It takes maybe twice as much observation time to find exoplanets at every position, because you essentially have to look this way and that way. Whether you do it as a smooth rotation or two different, it just takes about twice the amount of time. But you don't have to put the whole telescope up there. Now you only have to put this one little piece. So that's the trade-off.
Right. And I think about other missions that are kind of related. I think about, like, say, TESS or the upcoming Plato mission. Maybe you go a different route where the telescope is sweeping in one direction, looking at all of the stars, and then comes back around, and now it's tilted the other way and is looking for all of the stars, and then turns again. Like, I'm sure someone's going to come up with some sort of ideal algorithm on how to scan as many stars as possible.
Right. Maybe something like that, but you have to worry about the cadence because the planets will move during that time, right? So you actually want to do kind of both, is to look at it as it is now at several angles and then come back and look at it again, because you can have exoplanets that come in that are actually closer to the star at some points in their orbits. And maybe they're going around this way and you're looking at it. Sometimes it's too close to see, sometimes it's far enough you can. And on top of that, you probably want to trace the orbit. So going back a couple times is probably a good idea anyway.
Now, you also in your article proposed a triangular shaped mirror. So how does that work?
There's actually some confusion because the picture looks like a slice of pizza, and the caption says a rectangular telescope. And I've had, there's been a lot of confusion over that. Originally, we just had the rectangular mirror in the paper, and the referee complained because correctly, the referee said, if you do this, then you put your heat shield behind the mirror, but then you point this thing all over the sky. This heat shield behind it isn't always going to block the light from the sun. It's going to hit that secondary mirror. It's going to hit kinds of places. And so that triangular piece in there is actually the shield that's shielding the telescope, the primary mirror that's a little blade. It's, on one side, and the secondary mirror from the light from the sun. Because if you have a telescope that's looking in the infrared is the wavelength that from heat, if you get infrared light from that's the heat. And so if you heat up the telescope, it starts to glow exactly in the wavelength that you're trying to measure out, from the universe. And so that will obliterate your signal. So you want to keep it cold. And so you need that heat shield to shield it from the sun. And that big triangular thing is the heat shield.
Okay, so there is no triangular primary mirror or secondary mirror.
No.
But I'm sure you've would that work? Like, now we're looking at slices of a pie. Like, is there some value in other shapes? Like, now you've already broken all the rules. Where does this go from here?
Yeah, I don't know. So to me, it doesn't have to be rectangular. It could be more like a oblong, elliptical oblong shape, not quite corners on the edges of it. But I don't know about what you get from triangular, because what I'm going for is the largest distance, right? And you're not going to get any better resolution than your largest distance. So whatever that is. And then how many photons you get, how much light you get from it, which is also a problem with exoplanets, right? You want to get enough light that you can actually see something. That goes by the area. And so the two things that I'm most concentrated in getting the mirror shape is the biggest length and the area. And so a rectangle or something more oblong is probably the easiest way to get area and length, rather than a triangle, which at the same area gives you a shorter length.
But in this situation, you're sort of putting together both finding exoplanets, essentially analyzing stars to see if there are exoplanets there, and also having your telescope that is used to analyze the exoplanets and try and give some spectra on the atmosphere or whatever. But if we absolutely knew that there was a planetary system that we were really excited about, and we knew it was there, and we wanted to make the best possible telescope to observe that, could you just keep going in that direction? Just keep reducing the height and then use that to buy you more width? Could you make a 60-meter telescope that is only 30 centimeters? Would that give you images, or is there a certain point where it just becomes diminishing returns again?
So you can make it narrower and get a higher resolution, but at some point you're going to hit engineering constraints of making it, not vibrate and and all that.
Big flappy wings.
And
I can
then,
imagine.
and if you take all of the mass and you stick it very far out, and then you want to rotate it and then change its rotation and point it somewhere else, it does get a little bit harder. I'm not sure what the limits are of what we would be able to do. And I didn't try every single combination. I mean, it's possible that you would do better by, making it a little longer or a little wider, or a little thinner, or a little whatever. But we kind of played with the parameters a little bit and found what seemed like kind of a sweet spot for being able to get enough photons and being able to construct such a thing, and to be able to distinguish the exoplanet from the star. But there are a lot of, like you're saying, there are a lot of games you can play. I mean, I think if I knew there was an exoplanet there, I might want a different instrument to look at it. I mean, with this, we ask the question, can you characterize the atmosphere of the exoplanet to the extent that you can see if there's oxygen in the atmosphere, because that's a big one. That's a big one we want to know. And the answer is yes. You can look at just one of the infrared oxygen lines. Again, if you build a telescope for the infrared, then what you see is the infrared. You can't say I have an infrared telescope and I'm going to go look at the visible for a line I like there. It has to look. And so there are oxygen lines in the infrared that you can pull out and look at. And in principle, you could probably design the thing to in a separate observation, maybe look at a different infrared line and maybe look at some other biosignatures that people see in these atmospheres. But a lot of the lines in the signatures that we're used to looking at are more in the optical. And so, it might be easier once you knew where it was, maybe down the line, something like more like Habitable Worlds is looking for, that's more multi-purpose, maybe has different things, maybe something like that eventually. But I actually think if it's close enough, sending a probe is not a bad idea, actually.
Yeah. I mean, it sounds to me that, you know that you need that telescope that has at least the 21-meter baseline. And then the question is how much surface area gets you enough sensitivity to detect enough of the photons to let you see the atmosphere. And that will just define the height of the telescope to get you that overall surface area on your telescope.
Yeah, more or less correct.
You had a really, at the sort of, you proposed that this telescope in operation will find a staggering number of planets once it's in operation. That's the punchline, is that this thing will be a planet hunting monster.
Well,
give us a sense of how many planets this would be able to turn up in some amount of time, if they're there, assuming they're there, right?
So calculating how many exoplanets you're going to find is a simulation game. And so we started out with the idea we really want to find the exoplanets that are closer than 10 parsecs or closer than 33 light years, because those are the good ones that we can maybe go to. And there are only, you can count up, there are only of the order of 60 stars that are that close to the sun that are what we would call like the sun. So about the temperature and size of the sun. And you can make it be less or more depending on how you define like the sun. But, something that would not be throwing out all of these big solar winds and flares and things that would be exterminating, something like the sun. And then you have to guess how many planets like the Earth are around these 60 stars. And we were using software that was created for the Life experiment, actually, which was using an extrapolation from planets we've seen already with Kepler and other experiments. And they have different scenarios, but the scenario we chose, which is kind of the middle of the road, said we think there's maybe one habitable, terrestrial kind of Earth-like planet around each sun-like star. That's the estimate. So if that estimate is right, then what we're doing is good. If that estimate is wrong, then we're going to be off by whatever factor it's wrong by. And then we kind of said, well, all right, then how many of these stars are we actually going to be able to find an Earth-like planet around? And some of the ones that are further away and have a very small, you would be closer than an AU to be in the habitable zone. We had trouble resolving that even with the telescope we designed, and so we threw those out. And then we figured out what a reasonable observation plan is and what the likelihood that the exoplanet was going to be observable in any given observation, and kind of went through and did this. And we figured we could get about half of the ones that were out there. So we figured that we could probably reach the Habitable Worlds Observatory target of like 25 habitable planets within 30 AU within a reasonable, several year mission that we could find all that. So that's pretty good. And I want to say that, that some of the, a lot of the exoplanet finding missions that are out there are using something called the transit method to find exoplanets. And in the transit method, you see the star and then you watch the star until a planet comes around in front of it and blocks some of the light so it gets a little bit dimmer. But that will only happen if the exoplanet is going around in a plane that's exactly aligned with where you're looking. And so there are planned missions that expect to find Earth-like planets, but in order to find Earth-like planets, they have to look much further away to have a big enough volume of space that they're going to find an Earth-like planet that is also aligned with where we're looking. And so what we were trying to do was to find really the closest ones, the best ones to get, and to find, 25 of these habitable worlds. Yeah.
And I think that, it's the same ballpark that people are proposing for the Habitable Worlds Observatory.
Right.
Right. And the Life telescope.
Yes.
And I just did a quick calculation, and Webb has a 33-meter area mirror. Primary
It's about
mirror.
the same square. It's about the same area
bigger.
as, huh?
It's bigger. It's bigger than, if yours is 21, this is 33. So you're actually proposing a telescope that is smaller than James Webb, and yet
When I did the numbers, it was about the same. I'm not sure it's small. So it's comparable, I would say.
Yeah.
Comparable
I was sort of
to Webb.
assuming it's a circle and not hexagons connected to each other.
Webb,
so that probably.
Webb also has a big hole in the middle of it. So
right. Yeah.
I think
but it's about the same size. Yeah.
And
that's the size they're proposing for the Habitable Worlds Observatory as well.
Yeah.
And the Starshade.
Yeah.
Which is also part of the.
You have to put two up, right? So
yes. Yeah. Yeah. So that seems like a really elegant solution. Has there been an interesting response? I know we're sort of in between decadal surveys right now, and progress is going, but I wonder, have people think about telescopes?
I have recently, actually because of the press coverage from this article, I was contacted by someone who was very interested in it, who actually has been working for years on rectangular telescopes, but hasn't been getting any attention.
Right. So that'll help. Yeah.
So
Yeah.
I think through doing this, I'm starting to be connected with a very small fraction of the community that actually, some of whom have thought of this before and think
Yeah.
this is a great idea.
Yeah. Yeah. I mean, what I really enjoy about this, and like I said, I have a filter in my mind that's looking for this kind of thing, is just any idea that puts together all of the pieces that we have on the table: interferometry, coronagraphs, different wavelengths, different kinds of rockets, things that already exist, things that could be built, put them on the moon, and then put it together in some kind of form that makes this detection feasible, as opposed to pie in the sky. Like, I love the idea of the solar gravitational lens. Let's send a spacecraft out 550 AU and turn back and use the sun. But it's a complicated job to get a telescope out that far. If there's something that's sort of within the boundaries of what we've already done, this feels very practical to get answers to these kinds of questions. And so this is the kind of thing that I'm super excited about.
Yeah, well, that's exactly how I feel.
Yeah. I'd like to shift gears briefly and just give an update on your other telescope concept that we talk about, the one that you had sort of received the NIAC grant for. So it's been about a year since we talked. How is the project going?
So I think this is what has the main thing that so far has come out of that is this telescope. And I'll tell you how this came about is that I was working on the NIAC telescope and coming up with it. We have a primary objective grading, and we worked out the optics of how that works and put in an optical program, and then figured out at some point that because of the zodiacal light, and especially the exozodiacal light in the host stars system, because there's going to be dust. There's dust in our solar system. We don't know very much about it, but we figure there's probably dust in the system that we're looking at. And it was going to be such a high background that we really needed to get, we not only separate the exoplanet from the star, but we also needed to separate the exoplanet from the zodiacal light in that solar system. And in order to do that, in that particular system, we had to build another spectrograph in the focal plane of the first primary objective grading that would separate the zodiacal light from the exoplanet. And we came up with a rough, a design that might make that work, but it was difficult. It was a very difficult thing to build. And we just actually got a paper accepted on that that shows that you can do it, and then separate the light and then put your detector in, and it sort of kind of worked, but it was going to be, tough technology to build. And at the end of that experiment, we sat down and we said, okay, so we got it to kind of sort of work. And now I want to know what advantage we got from using that primary objective grading over using just a mirror. And so we plonked a mirror in to the calculations where the primary objective grading was. And that was a long, thin grading, because that's how you make gradings. But we just plonked the mirror in where that grading format was. And that's how this telescope was discovered. That actually, right, when you put the mirror in instead of the grading, everything just worked.
Right. So turns out people who had invented this telescope were onto something.
Yeah. So, but I think there are possibly, I'm still looking for other possible uses of the primary objective grading telescope, because it has features that a regular telescope doesn't have. And originally, when I started working on that, I thought that one of those features was going to be good for finding exoplanets, but I think that's not the best use for it at this point. And so I'm looking at possibly other ways to use that telescope that takes better advantage of the spectroscopic capabilities. And let me kind of explain a little bit of why the exoplanet turned out not to be a good application. So when you have a really big grating, the light that comes to you in the focal plane is inherently very high resolution. So you have a spectrum that you divide the light up from the object into very small wavelength bins. And so you can measure very accurately what the wavelength is that the light is coming to you. However, if you have a very faint object, most of those bins have no photons in them at all. And so you don't actually get a very high resolution spectrum from a very faint object. And so I think that in order to use that unique capability of the spectrograph to separate light, really it would be better if you had a target that was much brighter. And in addition to that, if you have a target that's much brighter and you don't have to separate the very faint zodiacal light background from it, then you don't need to have that second spectrograph in some cases. And so I think maybe we're going to reorient what we would want to look at with this. Just, you find out more and more about what a particular technology is capable of and what it's not capable of by really working out the details. And then sometimes your research takes this complete turn because, suddenly you stumbled into something else, which is what happened in this case.
Yeah. That's sort of like the best kind of accident. Heidi, what are you obsessed with right now?
Oh, I am obsessed with, this is taking a lot of my effort, is to work on this telescope. But then in addition to that, I'm really excited about the dynamics of the Milky Way galaxy and in how dwarf galaxies interact with, so we have our big fat galaxy has little galaxies that orbit around it. And those little galaxies are interacting with dark matter, and they're also interacting with the Milky Way disk. And so I'm really excited about understanding those interactions and what we can learn from them about dark matter, what we can learn from them about the history of the formation of the Milky Way, what we can learn about the shape of the disk and how much of the shape of the disk was actually is there because of these interactions. And so every time a dwarf galaxy comes in and it hits the disk, it can cause a little ripple wave structure in it. It can cause warping. It can cause flaring. It could even cause spiral density waves, spiral arms in galaxies. And so a lot of the things that we see when we look at a galaxy is the disk, and a lot of the formation that you see in the disk is shaped by dwarf galaxies coming into it. And so I've been thinking a bunch about those interactions, this dynamical, non-equilibrium kind of structure in our own galaxy.
I mean, when we think about the formation history of a galaxy like the Milky Way, it's assumed, if it's bottom up, then it came from all of these dwarf galaxies coming together to form this larger galaxy. And yet, if the Milky Way is surrounded by more than 100 maybe of these dwarf galaxies, then they're going to continue to have some kind of influence. And as you said, we can see thanks to the Gaia survey, we can see examples of galaxies, dwarf galaxies that were torn apart and added to the galaxy's mass. We know that the Milky Way's disk is warped a little bit, probably from some past merger, maybe the same merger as the Gaia Enceladus sausage, which is the most hilarious name. And so, like, is it more that the dwarf galaxies serve as a probe to help you understand the structure and the nature of the galaxy, or is it more that things are evolving and unfolding still this late after the Big Bang, and this process is continuing to sort of shape what the Milky Way looks like into the future, or both?
I think that well, that's a very long question. I want to start
Yes.
with one thing at the beginning of it, which is that the Gaia Enceladus merger traditionally is thought of as something that happened 10 billion years ago. And so that is thought of as something more that shapes the halo of the Milky Way, the outer part, more than it shapes the present day disk, although they do say that it may have puffed up the thick disk and made that. I actually don't agree with the people who have made those conclusions. My group has been famous for not agreeing with that understanding of it, and that I think that a lot of the stars that are ascribed to being part of that are part of a more recent merger, and not something that popped up the thick disk 10 billion years ago. But I do think that that both of the things you said of using dwarf galaxies as a probe of dark matter and looking at the effect that they have on the disk. So dark matter is sort of a big, we call a halo structure, but for us a halo is not a ring, it's a big sphere. So there's a big sphere of dark matter that the Milky Way galaxy is sitting in. It may be lumpy, it may be funny shaped a little, we don't really know. But you just kind of think of it as a big spherical lump of dark matter that the Milky Way is sitting in the middle of. And the only way we know that dark matter is there at all is because of its gravitational effect on things we can see, stars, more or less, or gas, but essentially things that produce light. And that's the only way we have so far to look at it. I mean, we've never seen it any other way so far. And so I think that we can push our understanding of dark matter further by understanding the effect that it has on dwarf galaxies and the tidal disruption of dwarf galaxies as they come near the Milky Way into these big streams of stars. And so in that case, we're looking at the interaction between something we can see, dwarf galaxies and their tidal tails, with something we can't see, which is the dark matter, and trying to understand how the dark matter in the original dwarf galaxy and the dark matter in the Milky Way galaxy have affected the creation of what we see, and therefore learn something about, the dark matter itself. In the case of the Milky Way disk, we can see all of the stars in the Milky Way disk, but they're dancing around in this funny dance that we don't know why they're doing it. And so in that case, what we're looking at is trying to figure out what's causing all these little substructures. You mentioned the Gaia Enceladus sausage, but there's also a very famous result called the Gaia phase space spiral, or the phase spiral, which is a correlation in the disk, where you see ripples in the disk, you see parts of the disk where the stars are moving coherently in one area differently than in another area. And if you put all those together, what's been seen in Gaia is that if you plot the velocity of the stars, say in the azimuthal direction around the disk, as a function of the height above the galactic plane and the velocity in the direction of the spiral plane, the velocity in that z direction, so called the ZVZ plane. If you plot it in that plane, you see actually a spiral. The stars are organized into a spiral. It's a very strange thing. When people first saw that, they were really surprised. But that correlation between position and velocity in the disk that makes that spiral is probably related to these same things we were seeing with the ripples and the wave-like structures and the different correlations with velocities in different places. And we're still trying to piece all that together as how they're related and how does it happen and what's the physics behind this whole phenomenon of disk we call disequilibrium, a non-equilibrium structure in the disk.
Very cool. And maybe a giant 21 meter by 1 meter infrared telescope might allow you to tease out some information from that. Heidi, absolute pleasure to talk to you. I'm sure I'll be talking to you in about another month when you come up with a new telescope idea. Yeah. But if not, good luck with both your work to develop new telescopes and, of course, your attempt to understand the structure of the Milky Way. Thanks for taking the time to chat with me today.
Okay.
I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bode, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, David Veribaf, David Gilton, David Matz, Evan Pro, Greg Feely, Hudson Ward, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Switz, Michael Purcell, Modso, Paul Robach, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fowler-Munley, Team 49, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So as I mentioned in the interview, these kinds of topics are catnip to me. I'm really excited about ideas for next generation telescopes, both land telescopes as well as space-based telescopes, ones that somehow get you a solution to the question, how can we observe an Earth-sized world orbiting around a sun-like star within the habitable zone of its star and be able to detect some kind of biosignature on that planet? And that we know that it's going to take a bigger telescope. It's going to take different kinds of wavelengths. It's probably going to require a coronagraph. But we have a lot of tools at our disposal already, a lot of big telescopes that are in development right now, and a lot of great ideas. And it's those great ideas that I get really excited about. And whenever I see them, no matter where they are, that's where I reach out and try to do an interview with the people who are behind it. And I know a lot of you enjoy that as well, because it's not about these sort of theoretical pie in the sky ideas for what would some telescope look like a million years into the future. What is something that we can build that is within our capability, that doesn't introduce a lot of technical uncertainty, that gets us closer to that goal of finally answering the question, are we alone in the universe? And hopefully this is another step along that way. All right, I hope you enjoyed the interview. We'll see you next time.